Okay. Okay. So sorry about the trouble. I don't know why it happened. I'm going to talk about some joint work with U.A. Mariah and Tao Li. I can see from the title, we're trying to prove the Berge conjecture for tunnel number 1 knots. Okay, so the question started as a dense surgery question. You can ask if you have any given 3 manifold, and you can ask what knot can produce length space by doing dense surgery on it. So let me give you some example. For example, all the torus knots have this property, and also the so-called Berge-Gabai knots also have this property, and those are knots that lies in the solid torus, and they admit non-trivial surgeries and produce a solid torus. So you can embed the solid torus in S3, for example, and because it doesn't change the solid torus, certainly it doesn't change. So the S3 become length space, and those knots are sort of like a one bridge knot. You have most of the knots are embedded on the boundary of the solid torus, but there's like one bridge over it. There was a very nice observation by Berge. Berge observed that if you take any genus 2 Hilbert surface of S3, and if you draw a simple closed curve on the genus 2 surface, and if this curve is so-called doubly primitive, so that means it's primitive in both handle bodies. What that means, primitive means you have a compressing disk, this blue disk that intersect this knot in one point. So that means this curve is a primitive curve in this handle body. So if this curve is primitive in both handle bodies, then if you do a dense surgery and set the slope to be the same slope of this surface, because if you do a dense surgery, you add a 2 handle. Now, if you imagine this surface, if you add a 2 handle to this surface, then you sort of fill in this hole, you become a solid torus, because if it's a primitive on both sides, so the both sides survives as a solid torus, a solid tori in the surgery manifold. So this manifold has to be a length space. So whenever you have a curve like that, you always have length space surgery. And also here I mentioned the original observation for S3. This observation doesn't have to be in S3. If you have any S3 manifold that has genus 2 Hilbert surface, then a doubly primitive curve, it always gives you a knot that produce a length space. So the conjecture is a beautiful conjecture of Berge said that's always the case. So the conjecture is if you have a knot in S3, if you have a dense surgery that will give you a length space, then this is always doubly primitive. So the most recent progress on this conjecture came from the Hilbert flow homology. For example, Yi proved that if you have a knot in S3 that give you a length space after dense surgery, then this knot is always fibered, because all the Berge knots in Berge's list, I forgot to say, Berge compiled a complete list of several groups of knots, and that's all the he proved that's all the doubly primitive knots, and he also had a list of all possible length spaces they can produce. And also my colleague Josh Green proved that if you have a length space, if the length space can be obtained by dense surgery on knot in S3, then this length space must be on Berge's list. And also, you can generalize this type of conjecture to other three manifolds. For example, a conjecture of Josh Green and Baker, Barker, and Lacona. They generalize this to S2 cross S1, and this also have some very strong evidence. If you have knot in S2 cross S1, if it's admit length space surgery, then this knot must be doubly primitive on a genus 2 Hilbert surface in S2 cross S1. Now we come back to tunnel number. What is the tunnel number? So the tunnel number is closely related to Hilbert splitting of compact surfaces. For a surface with the boundary, usually a Hilbert splitting is an embedded surface that bounds compression bodies on both sides. What's compression body? For example, here I draw this only compression body that's we're going to use in this talk, which is the genus 2 handle body. Then if you remove a core curve, the neighborhood of the core curve, this is the compression body. And in general, compression body is you start with a surface, then you just add 2 and 3 handles on one side. That's a compression body. And every 3 manifold, the orientable compact 3 manifold has a Hilbert splitting. And for knot, a tunnel number of a knot, here I draw a trifoil. For example, this red arc is what is called the unknotting tunnel, because if you add this arc to this knot, you get a graph, and the complement of this graph is a handle body. So that gives you a Hilbert splitting of the knot exterior. And if the knot we mentioned, the doubly primitive knots, they have tunnel number 1. So you only need to add one tunnel, one unknotting tunnel to make the complement a handle body. So tunnel number 1 knot, so its exterior has Hilbert genus 2. So all the doubly primitive knots has this property, and in particular, the reason for that because it's doubly primitive. So that means this curve intersects a compressing disk in just one point. Now, if you push this curve into either of the 2 handle body, and then you can make this handle body a compression body. If you drill out this knot to give a compression body, you can push on either side to give you, that's going to give you a Hilbert genus 2 Hilbert splitting of the knot exterior. So the main theorem I'm going to talk about is if you have a knot in a 3 manifold, and this manifold can be S3 or can be S2 cross S1 or the connected sum of S2 cross S1 with the length space. And if this knot is tunnel number 1, and if it has the length space then surgery, then this knot must be doubly primitive. So that's I can view this as one piece of the Berge conjecture. So the remaining piece would be if you have a knot in S3, you can show the conjecture is if it has a non-trivial length space surgery, then this knot always has tunnel number 1. So if this conjecture true, then plus our theorem, that can approve the Berge conjecture. So here I want to make a remark is that you can ask this question, sort of analog question of Berge conjecture for any manifold, as we mentioned, as long as this manifold has genus Hilbert surface. If you take any doubly primitive curve on the surface, then you always have a length space surgery, and you can ask whether or not the Berge conjecture is true for all such 3 manifolds, and the answer is no, because there are examples of knots on, for example, some length spaces, and this knot doesn't even have tunnel number 1 even. So that's true. So you can see here those the manifold M cannot be any length space, but we proved that at least for S2 cross 1 and this manifold, then you have this property. The reason we require this manifold to be the connect sum of S2 curves as one. And length space is a couple of theorem in the 80s. The first theorem is by Homa, Ochiai, and Takahashi. They proved that if you take a genus 2 Higard diagram of S3, then this diagram is either standard or it contains a wave. And Nagami and Okita generalize this theorem to connect sum of S2 curves S1 and the length space. And what is a wave? A wave is, if you can talk about a wave in a handle body, basically. If you take, let's say you have a complete disk system, here I have two black compressing disks. Now this blue arc is a wave. So this arc is disjoint from the other disk and also on the same side. For example, if you do like a boundary compression on this disk, you end up a parallel copy of this disk plus another disk, and that resulting disk would be this compressing disk. So that's operation is called a wave move. You replace this compressing disk with this new one. You get a new system of compressing disks. So that's a wave move. And for a Higard diagram, we require this wave to be disjoint from the meridians on the other side. So you have some curves that bound the disk on the other side. You have a Higard diagram. You have another pair of curves that bound disk on the other side that we require. If this you have a wave that disjoint from all these curves, then you have an obvious simplification. You can do a wave move to get a simpler Higard diagram. So those two theorems basically give you an algorithm. If you start with any Higard diagram of either S3 or connect sum of S squared 1 and the length space, then you can, by doing wave moves, you can change this Higard diagram into the standard ones. So that's why it's so special about those manifolds, and that's precisely the reason we use those manifolds. That's because of the theorem. So that's why those theorem, why those manifold. The starting point is a fairly straightforward lemma. If you take a knot in the manifold, either S3 or one of those manifolds we considered, if this knot has a non-trivial length space surgery, then either this is a torus knot or the surgery slope is the integer slope. For S3, that follows from the cyclic surgery theorem of a color Gordon, Luke, and Shalen, and for other those manifolds, so that follows from the theorem of Boyer and Zhang. So they prove a version of this cyclic surgery theorem for reducible manifolds. So not just those manifolds, all the reducible manifolds. Okay, so that's the starting point. So we can assume the surgery slope is the integer slope. Okay, now because the manifold, the knot is assumed to have tunnel number 1, let's start with the genus 2 Higard surface in the knot exterior. In the knot exterior, then we can view this dual knot. So this knot in the length space. We can look at from the point of view of the length space, because this Higard surface also give you a Higard surface of the length space. Now you have genus 2 Higard surface of a length space. So this is stabilized. So you have a stabilizing pair. You have this disk, another disk, but this disk intersects this knot, this dual knot. So this red curve is L prime, is a dual knot in the length space. So you get basically punctured disk. So that will give you a planar surface. And this planar surface intersects this disk on the other side in one point. It's sort of similar to a stabilizing pair. It follows from the integer slope. It follows that if P is the annulus, then this has to be doubly primitive, because on the because they have this is already a Higard surface. On one side, this is already primitive, and if this is the annulus, you can see this. You have this black meridional curve of the of this K prime, and that's give you a curve on the surface that intersects the disk on one side. But because this is the integer slope, this meridian for the knot in length space is actually isotopic is to the knot. So that means there's going to be a primitive on the other side. So if P is annulus, you automatically can prove that this is doubly primitive. So the starting point is let's start with this PD pair. Let's try to make P an annulus. If you can do that, then you prove this Berge conjecture for tunnel number 1 knot. However, this is not that simple. There's some tricky things. For example, we start out with an arbitrary genus 2 Hilbert surface of the knot exterior. But there are examples of Berge knots that if you, because of some Berge knots has multiple different unknotting tunnels. If you pick a different unknotting tunnel, that give you a genus 2 Hilbert surface, but it's possible this knot is not doubly primitive on that surface, but it's doubly primitive on a different genus 2 surface. Okay, so that's a tricky point. So to take care of this issue, we have to do some operations. So this is one of the operations we do. Let's say we start with this planar surface disk pair. You start with this pair, and then you can sort of pull this strand of this knot out. So now you add a handle. It's like doing a stabilization. You change this Hilbert surface from genus 2 to genus 3. Now let's try to pull this knot, pull this handle longer and longer. For example, if this knot here come back and get connected to this strand, you can keep pulling. And as long as this pulling does not affect this disk, you can keep doing that. And if you can just successfully pull this O out, now this planar surface become a disk, you get a stabilizing pair. You can fill in this hole and get back to a genus 2 surface. But now the new genus 2 surface has an annulus disk pair. So that means this is doubly primitive. So you change the Hilbert surface to a new Hilbert surface, but this knot is doubly primitive on that Hilbert surface. And by the way, this is in the length space, not in S3. So sometimes we have to do this operation because otherwise it's impossible to prove this. Okay. Now, because we are trying to use the theorem of Homa, Ochiai, and Takahashi, and Nagami and Okita, so let's try to find a nice Hilbert diagram to the manifold. That's either S3 or the connect sum of S2 cross 1 and the length space. There's some standard thing to use. For example, first let's start with a planar surface PD pair. So for those, if you take a planar surface and the disk pair, now you always have another disk. You always have another disk. So let's say this is D, you have another disk E. Okay, we can pick this disk E, D, and this disk E to be a maximum set of disks. And let's say this, we use delta to describe the boundary of this disk and epsilon to describe the boundary of the other disk. So that's the standard pair for the handle body part. Now for the compression body part, there are also some standard thing to use. You have this one sort of unique non-separating compressing disk. So the boundary we call gamma. And you have some curve alpha and beta that bounds annuli in the compression body. Let's use alpha and beta, either alpha or beta as a meridian for the handle body in S3. So we get two complete set of disks, and let's look at the Hilbert diagram. For genus 2, the beauty of genus 2 Hilbert diagram is because they have this hyperelliptic involution, and the Hilbert diagram is rather symmetric. For example, here, let's say those two curves are glued together, and so this A, those numbers are, so this is the white-headed graph. So the numbers means the number of copies of those type of arcs. So because the involution switch those two curves, so it doesn't matter how many copy here, you have that number of copy here. So you have this symmetric picture given by the hyperelliptic involution. Okay, so that play a very big role in our argument. And also, let's the picture we're trying to look at is we take this Hilbert surface, genus 2. Now we cut this surface open along the boundary of the planar surface. Okay, so if you cut open that, let's look at, for example, the planar surface. This is in S3 picture, this planar surface, and it's no longer a punctured disk. You have a planar surface, the boundary slope is the surgery slope, is an integer. So the planar surface is going to intersect this disk bounded by gamma, and you can easily find a curve gamma, a segment of gamma, intersect this boundary P from the same side, and the hyperelliptic involution give you, this curve give you another curve. And also we can sort of view this, this is a twice punctured torus, which is, we cut this genus 2 surface open along this curve. And we can view alpha, beta, and gamma, all those type of vertical disks, either vertical in the rectangle or the vertical in one of the two annuli. Okay, so we look at the picture of alpha and beta and gamma from this picture. And also we look at the epsilon and delta. Remember, delta is the boundary of the disk, the PD pair. So the delta intersects this boundary P in one point. So this red curve is the example of delta, and this blue curve is the example of epsilon. Epsilon is disjoint from this planar surface by choice. And we cook up a complexity, and the first part of the complexity is we look at this alpha and the gamma. So that's in the Hilbert diagram. We look at those arcs in this surface. Look at how many of arc actually intersect this D. For example, if you take this arc, so those arcs do not intersect this red arc, disjoint from this D. Okay, so that's the number of the arc intersect D is one complexity. Another second complexity is just the intersection number with D. And the first lemma is, if this complexity is really small, then we can do the operation we mentioned. We can do a stabilization, and the unstabilization, we can find possibly a different genus 2 Hilbert surface so that K is doubly primitive. So for very small complexities, if this K, then you have doubly primitive, this K is doubly primitive. And also there's some nice observation. For example, this delta and epsilon do not backtrack. So this is an example of a backtracking. They'll come here from this from this rectangle and come back to enter from a different side. You have this direction from one side. I go back to the same direction. So this is a backtracking. There's no backtracking. The reason for that is either you can do a boundary compression, or you can find something we call blocking edges. What's a blocking edge? Those are two types of edges. If in your Hilbert diagram, you see an arc, like a pair of some arcs connecting our plus side to the minus side, plus side to the minus side, and you can guarantee that there's no wave in those in the Hilbert diagram, because if you take a wave, that's going to be something like this. This wave have to intersect this blue arc, so there's no wave like this. And here, if you have this type of arc, there's no wave either. And you may say, well, why? Well, maybe there's this is going to be a wave, right? But because of the hyperelliptic involution, if you see those two type of arc, you automatically see those two type of arcs. Okay, so you have no wave at all. If you have this two of those, there's no wave at all. So if you see this backtracking, you can find those edges sort of blocking all the waves. Then you can prove the theorem this way. Okay, and the general strategy, let me quickly finish this. First, let's say, because we look at this boundary of D, which is the curve delta. That's the curve intersecting P in one point. And because there's no backtracking, we can pinch all the vertical arcs to a point, then we can make this a train track inside the genus 2 surface. And because this is punctured, this is intersection point we call X. Those 2 points are the same point once we glue top and bottom together. So, and for example, this picture, if you pinch those vertical arcs together, you get this train track. And there are 3+1 cases. So basically, 3 cases. There's a special case in the background. The first case is depend on the train track. The complement of the train track could be a one-punctured torus. For example, if you take this train track, the neighborhood of this train track is a one-punctured torus. So the complement in the genus 2 surface is also a one-punctured torus. And you can take this train track. If you have this train track, the boundary of this train track is an annulus, and you have 2 cars on each annulus. So this is should be viewed in the genus 2 surface. It's not on the plane. And also, if you have really the curve really winding around so much, you could get the complement to be a hexagon. Those all 3 kind of configurations for the train track, for the complement of the train track. And also a special case which called the long path, because so that's the case when you have arc winding around a lot of time. So this is a special case. You have to deal with that, deal with this case totally differently. And then it doesn't change either one of those 3 cases. It's just because if you have winding around, then it makes everything special, everything different, actually simpler. Okay, so those are the different cases. So the idea is the game is either you try to find a new PD pair or find a new Higar diagram to give a small complexity. You can reduce the complexity, or you can find the blocking edges. So there's no wave. So that means the manifold cannot be one of those manifolds. Then you're done. Or there's a special case is you can prove this K is a Berge-Gabay knot in a certain technical setting that you can find some special disk. Then if you compress this disk, you change this genus 2 Higar surface into a Higar torus, and it's not living in the Higar torus, and the density of knot on this knot also give you a Higar torus in the length space. So that means the density of this knot give you a solid torus. So that's a Berge-Gabay knot and also doubly primitive. So either one of the 3 cases. So that's the strategy. So I'm running out of time, so I'll stop here.
Thank you so much for such a nice talk. And well, anyone has any question about the topic?
Tao, I think I have a question. It's fairly broad though. This looks really neat. But what I'm wondering, how many choices you're making, right? You're starting with a diagram and you're starting with a knot and you're wondering whether or not it's doubly primitive.
Right.
Starting out with, discs, and it's not doubly primitive with respect to this Higard splitting. And then there's maybe, let's see, wave moves, right? You mentioned all of the options. You sort of, are there wave moves? But is that sort of canonical, or are you making choices? Like how is this?
Well, it's not canonical at all, because we divide this into several cases. It turns out to deal with those cases, although it's fell under the same kind of strategy of considering those train tracks, but the details are actually surprisingly quite different, because to handle each case, we sometimes have to use totally different technology, and so it's not it's not canonical at all. So it's sort of like a piece by piece. We try to build this thing and throw everything at it. If it doesn't work, we try to find another thing. And in the end, somehow each case, its case works.
Okay. Yeah. Okay. So you can do it, but computers can't. There's no algorithm.
Yeah, that's well, you had to. A lot of time we just stare at this picture and see what can we do to this picture? And if you can do that, how about that picture? And it's sort of painful in a way.
Okay.
So what's known for higher number tunnel number? I mean, for higher tunnel number.
Yeah, that's a good question. So, well, one thing to deal with the higher genus case is, well, first of all, you cannot just copy this method because that's very restrictive. Because one of the things we use for the genus 2 case is you have this hyperelliptical involution you can use. But you do not have that in the higher genus case. That's one thing. So you cannot just hope you can do this for higher genus surface. But because you do not need to do this in higher genus, because once you know this for tunnel number 1 case, what you need to prove is if you have a knot that have a lens-based surgery, then you want to prove this knot turns out is tunnel number 1. For example, in a certain very special situations, remember this construction we talk about, it had to do one stabilization and one destabilization. And if you have a higher genus, sometimes, very special times, you could have a situation that you can do a stabilization once, but do a destabilization twice. You can reduce your Higard genus. If you can always be able to do that for higher genus. Because higher genus, you have some more degree of freedom to do things. If you can do that for higher genus, then you can reduce that to a tunnel number 1.
I see. Thank you. Okay, so thank you again. Thank you so much. Such a nice talk.
Okay. Thank you.